Audio picks up. I don't know how to test it. There's no sound meter. Well, I guess we'll see it later. What was the question that we asked on Thursday? Why did I have you guys do an experiment? This experiment that we did on Thursday. What was the whole point?
What is the probability of getting heads?
When you do what, Mary? Absolutely. When you spin a penny and let it fall. So you spin a penny, let it fall. What's the chance that you're going to get heads on a coin spin? Not a coin flip where you stop it, put it on your hand, but a coin spin and allow it to fall. Awesome. So, and the thing is that we did finish the answer at the end of the day on Thursday. I want to revisit that answer today and kind of deconstruct the answer, because the answer was gotten with technology, which is fantastic. We're going to continually do that, but I want to make sure we deconstruct where that answer came from and understand where this magical result came from. Now, I want to take a step back a little bit and talk about what exactly the form of the answer of that question needs to look like. We often say when you flip a coin, it's 50-50 whether you get heads or tails. And why do we say that? Do you remember why it's 50% heads when you flip a coin? Because there's two outcomes, and the outcomes are yes, yeah, independent, exactly, independent, and also this is not necessarily this. What you guys are doing is a very good job of describing a binomial experiment, which is perfect, but this is a very special binomial experiment. What assumption are we making when we say heads is 50% likely and tails is 50% likely?
It can't land on the side. So.
Good. There's only two outcomes, and those two outcomes are equally likely. Good. Can't land on the side. Even if it could be equally likely. Actually, I tried that experiment a few years ago. Somebody asked, you ever seen a three-sided coin? I'm like, well, yeah, every coin is three-sided technically. But what they asked was, they asked again, they said, can you make a coin so that when you flip it, it's just as likely to land heads or tails or on its edge? So I was like, well, hell, I don't know. Because that's tricky. Heads and tails are symmetric, but the edge has got this weird curve, surface. So I called my dad on the East Coast. I said, dude, you have access to like machining equipment. Can you build me a few of these? So I measured what a quarter was, and I had him make me a variety of widths of quarters out of aluminum, which is a bad idea because it bends too easily. And then I had a bunch of kids in class start flipping them and seeing which ones. And we never did come up with a positive answer because it's extraordinarily tricky to be able to say, okay, now it's a third, a third, a third. Because you can't just assume all three sides are equally likely. You have to show it experimentally that they're equally likely. And that ties back to what we're doing right now. We can't assume, well, we can go in assuming that it's 50-50. And then the experiment could either support or refute if it's 50-50.
What was it shaped like?
They were like a tall coin. If I remember, I'll bring them up to class on Thursday. But imagine a quarter, like a stack of quarters, that varying heights. That's all just one big cylinder. That's what they look like. Like one was as tall as it was wide, like a big square cylinder, hard to flip. And then it becomes tricky how to flip it so that it doesn't bias on the spin. Like a coin flipping heads and tails, you don't mind if it spins this way because each one is equally. But if you have one going like this, I started flipping it kind of like this, and it started bouncing off and hitting people in the class. And I just, but anyway, it's tricky. This is not so tricky. There's still two outcomes. They're independent. If you land on heads, you haven't landed on tails. I'm assuming, and I think it's a fair assumption, as Karen's point is, they're independent probabilities. I think that's fair. Whatever the chance of heads is, the complement is the chance of tails, but the question is, what is that chance of heads? And in order to answer that, we can't just give an answer. It's not 43% or 44% or 45%. We have to, and this is the title, if you will, of the section. We're estimating a population proportion, which I'm calling a little p, by using, this is parentheses, by using a confidence interval. Is it okay if I go ahead and start calling that CI for confidence interval? That wasn't enough yeses. I want to put confidence interval underneath of it for once. Confidence interval, that's a T. Wow, it's hard to write vertically. By using a confidence interval around P hat. Remember what P hat is? Not what the nurses made me wear in class. Remember what P hat is? Awesome, Jess. It's your sample proportion, which is tied to your population proportion. This is called your best unbiased estimator of what a little p without a hat is. Little p without a hat is the actual probability that you're going to spin heads. It's the actual chance that you're going to spin heads is little p. But you don't know that. You don't know what that is. So the best estimate you can get is little p hat down here. Is little p hat down here. Fair enough? Now, but what's the problem with the fact that it's a sample proportion? What's the problem with that? By itself, is it okay to just say sample proportion is p hat? Is it okay to just say p hat? Whatever that is, that's the answer. That's how likely it is to get heads. I'm going to pull this down for just a second. I'll put it back up. I've seen a couple of heads shaking no. Some of you might not know how to answer that just now. For example, here are the results of this experiment. Here are the results of this experiment from 2006 to the present day. I do it every term, usually at least once a term, if not more. P hat values that I have gotten in the past: 43%, 39%, 42%, 43, 43, 45, 43, 43, 38, 39, 42, and you see, they vary. They vary. 45 down here, 48 right here. Here's you guys. Can't quite see it. You guys were 40%. Doesn't seem right.
44, actually.
D34, yeah. Oh, hang on a second, increased decimal. Oh, that's decreased. There we go, 44%. That was weird. So you guys were 44%. So why can't you just do an experiment, get p hat? By the way, that 44% came from where? How do we compute that value?
189 divided by 430.
Perfect. 189 divided by 430. That's from over here. Let's back up for a second. From the ratio of x to n. P hat is the ratio of x to n. Which, I mean, all you got to do is run your values through. 189 out of that 430, which ends up being about the 44%. And we did, I mean, again, I think we used the TI to do this last time, but I think everybody remembers this from basic probability. That's the chance in our sample that we saw heads. It's a perfectly descriptive measure. Here's our sample of 430. We got 189 heads. Therefore, in our sample, the chance of heads was 44%. Boom. Why can't we just say, okay, if I want to know what the actual parameter value is for spinning heads, why can't I just call it 44%? Say that again. Ian, was that you? Say that again. Margin of... What? Why you have to put a margin of error on there, friend? Or anyone for that. I'm sorry, not to pick on you repeatedly.
If you try the experiment over and over again, you'll wind up with different results.
Which we did. Every time I do the experiment, I get slightly different results. These all say 43, 43. They're not exactly 43. If you actually form the ratios and increase the decimal enough, you'll see that. Ish, 43-ish. But every single time you run the experiment, you're getting different results every single time. So how could you say that your experiment, your p hat value is exactly equal to little p? It's not. It can't be exactly equal to little p. It's going to be equal to little p-ish. And the ish is where the margin of error kicks in. Absolutely. So let's do this one more time. I'll put this up and shut this down temporarily. We're going to come back to that to prove a point later. Let's use technology to get that margin of error around p hat. And then I want to come back and reverse engineer that margin of error, because I want you to understand where it's coming from. It seems a little bit alien. It just pops out like, okay, there's a margin of error, yay. But it doesn't explain where it comes from. I need you to understand where it comes from with one example, which will, like I said, we'll reverse engineer this one. After that, once you understand where it comes from, we can just use technology every single time. So let's run the machine, get the actual answer for what is the chance of getting heads on a coin spin. Go ahead, Michael.
So, I mean, then roughly P would be equal to P hat plus or minus within the margin.
That's exactly what we're doing right now.
Okay.
Yeah, we can't say it's 44%.
Right.
We can say we believe that little p is between 44% minus the margin of error and 44% plus the margin of error. And that's what the machine's going to get for us right now, and we'll reverse engineer it momentarily. Okay. Yeah, we'll get to all that, promise. So let's fire up the machine. I'm going to place this...
Are you talking about the stuff from last week?
Yes, exactly. That guy right there.
1.399.
Oh, no, that's not a margin of error. Very good, Chris. That's one of our stats. That's the standard deviation of the sample.
Yeah.
Now, very important point to be made here. Not to memorize, but just to be made. We ran one of our stats on this sample. We did. We ran one of our stats to get the average number of heads per 10 trials. And I think it was 4.4. 4.4 heads per 10 trials. Which, if you convert that to a percentage, is 44%. That 1 point, whatever you just quoted, is the plus or minus average number of heads per 10. So what you're talking about is actually an average value, where I'm talking about a percentage value. So I need a different computation for that. I need to not use mu or x bar, and instead use proportions with binomial. So it's the difference. This is why I only did two distributions in 243, the binomial and the normal. The binomial will serve us well here. The normal will serve us well with averages, which we'll start on Thursday. Great question, great question. But even if we were just well, I'll hold that point for Thursday, because I want to come back to that. That's a great point you just brought up. That's a purely descriptive term. We need an inferential term, something that's predicting what's going on in the overriding population. Great. We'll come back to that like in 48 hours-ish. So, here, I'm going to take this off just to clear some room. I'm still trying to work out the fisheye issue with this thing. Make that a little bit big.
Put it between the seats on the wall.
Well, that's a great idea. I thought about that too, but then I get neither board optimally. If I put it here, at least I get this board optimally. So, yeah, I thought about that, Zoe. It's a great, and if I could somehow get, the problem is the fisheye goes off to infinity very quickly. So I'm trying to maximize the use of this, and then I'll swing it that way if we use that board, which we will here momentarily. Yeah, this might not be the best camera to use. It's all part of the experiment process. All right, so remind me where we're going to go to get this cool shortcut. Stat. Tests, which is the first time we've ever gone there, and this is pretty much where we're always going to go in this class. Pretty much. Tests. I just put new batteries in. Why is that so dark? And out of focus. Oh, that's not bad. Tests, and then we got to go find the one that's called one prop z int. Ash, yes, one prop z int. Go look for it. Oh, there it was. One prop z int.
B?
Mine's A. Yours might be B. It depends on what model you have. One prop means single proportion, which is what we're estimating. Single proportion. Int is for interval. Z will make sense momentarily. Promise you on that one. So we're going to go one prop z int. Oh, my data's still in there from Thursday. We had 189 successes out of 430 trials. That confidence level will make a lot more sense as we go through today. I want to spend the rest of today kind of talking about what that confidence level actually means. You've already seen it without realizing you've seen it in that Excel spreadsheet I just had on the board. We'll get back to that. Then you just scroll down to calculate, hit enter, and I believe this is the same. We rounded this off to answer the question, what is the chance of heads on a coin spin when the coin is allowed to fall? We cannot just say that it's 44%. Well, we can say that. We shouldn't say that. You should say it's 44% plus or minus the margin on our sample average 44%. But in average, what we're trying to do, this is what I want to come back to what Chris said about looking at S. We don't want to limit ourselves to just our sample. We want to talk about the entire population. So what we want to say is, okay, what is the range of possible values that I feel confident in saying that could be in the population? So, in other words, I'm 95% confident, more on what that means momentarily. I'm 95% confident that the proportion or the percentage or the probability of heads is at least 39%, but no more than about 49%. So that's what we're going to say numerically. It's at least 39%, but no more than 49%. That's my comfortable 95% confident response to what is the chance of getting heads on a coin spin. It's at least 39%, but no more than 49%. So that represents, that interval right there, represents a swing of how many percentage points? How many percentage points is that? That's 10. That's 10. Now, if you remember back to last class, a confidence interval, much like it was in 243, consists of a center value plus and minus a set of what I was calling wings, which Ian more concisely called a margin of error. So in other words, this confidence interval consists of the center value of p hat. So this number here, this 0.39, is p hat minus that margin of error. And this number here is p hat plus that margin of error. So knowing that, what is the value of the margin of error? What is the value of the margin of error? If this guy is that minus it, and this guy is that plus it, it's got to be 5%, doesn't it? 44% minus 5 gets you, we're ishing. We're ishing, because it's not exactly 5, but it's close-ish. This minus 5% gets you down to 39%. This plus 5% gets you up to 49%. See what I'm getting at there, friends? So the question, of course, is, we know that p hat is 0.44, and the margin of error is about 5%. The question I'd like to attack right now, that's address and attack at the same time, attack, new word, copyrighted, can't use it, 5 cents please. What I want to talk about is, these are the jokes, kids. What I want to talk about is where that 5% came from. Where that 5% came from. How did the TI know that the margin of error should have been 5%? Oh, Darla, go ahead.
Is it because we entered with 95%?
That's unfortunately a coincidence. That's an unfortunate coincidence. It won't always be, it's dependent more on your sample size. It has something to do with that number 95, but not the actual direct 95.5. Wouldn't it be nice if it was that easy? Unfortunately not. That's a numerical coincidence. We'll come back to that momentarily. Thank you for that. Michael?
95% is, it's where 95% of the data exists.
Can I rephrase that?
Sure.
I love what Michael just said.
It's within 2 standard deviations.
Good. That's exactly what it's tied back to, which is why, Darla, it's not wrong to say that 95% has something to do with it. To 95%, just like you guys remember from 243, is all about 2 standard deviations. It's all about 2 standard deviations. What the trick is, it's interpreting when I say I am 95% confident that it's between 39 and 49. What that means, and hear this, don't memorize it, hear it now, and I want to keep saying it over the course of the entire term. What it means is, if I run this experiment over and over and over and over and over, what it means is 95% of the time, the intervals that I get from all those repeated experiments are going to trap the value I'm looking for. Remember, I don't know what the probability is of spinning heads. I spin heads, the coin falls down, I keep track of my experiments. What I don't know is what the actual probability is of spinning heads. I want to know, that's the whole point of doing the experiment. What a 95% confidence interval says is, if I do the experiment 100 times, 95% of those intervals will contain the value I'm looking for. It doesn't tell me what the actual value is, but it gives me boundaries 95% of the time of how low and how high it can go. Now some of you might be sitting there going, how is that helpful to us? How is that helpful to us at all? Well, I've gotten enough data now over the years, I think, to show you that it's actually fairly helpful. There's my data. Now I've done this experiment-ish 20 times plus or minus some experiments. So 20 times is great. The reason I like 20 times is I haven't done it 100 times yet, by the time I retire maybe. But I've done it 20 times, which means 19 out of 20 should be 95%-ish. So in other words, 19 of those 20 intervals should contain the true value of the probability of heads. And now, the thing is, I still don't know what the probability of heads is. I still have no idea what the chance of heads is. Because I don't know. I mean, it's a penny spinning, letting fall. Physics is happening. However, look at those intervals. When I first posed this question last week and I said, what's the chance of spinning heads and having it fall down? One of the first expressions I got was 1/3, followed by 1/2. This can disprove the 1/2 with 95% confidence. Can you see how this can disprove that it's, I can pretty much say with 95% confidence that it's less than 1/2. Can you see how? What do you think of Ben?
What I'm thinking is just because the standard error, it only goes up to 0.48.
Oh, good. You're looking at our particular one. Yeah, our particular interval definitely disproves, if you will, 0.5. Because our interval, remember what we said? I'm 95% confident that the percentage of heads is at least 39%, but no more than 49%, which is 1% off from 50. Which means I can now also, rephrasing it a different way, it's at least 1% less than 50%. It could be more, based on our sample data with the standard error. Well used, by the way, with the standard error back there. Very nice. Ian, what are you thinking?
Do all of those p-hat values have 95% margin?
Yes!
So
Every single one of these is based around 95%.
the highest 95th percentile would be 56. if one
Yes!
was over there.
Good. Ian's going through the values and seeing that this, where was it? One was very high. 51, that one right there. 51% plus or minus, I forget what the margin of error is. Looks like it's about the same as yours, plus or minus 5%. Now, here's the thing, Ian. Not every one of those intervals has a plus or minus 5%.
Oh,
They're all 90. This is where, back to Douglas' point. They're all at 95% confidence, but the margin of error fluctuates depending on this guy right here. Now, you might not have caught that, and it's okay. You'll see why here momentarily. But when your sample size is larger, say 400, look at that one versus, say, 190. Follow my fingers over as we check those out. Notice the one that's built around the 400 and the one that's built around the 200. Notice this one's narrower. That means you have to accept a smaller margin of error with a larger sample size. More on that why as we go through today. Very, very good. They're all 95% though. Now, but the 95% basically ties into the interpretation. 95% of the time, 95% of the time, the interval that I've created is going to trap what I'm looking for correctly. The trick is I don't know the value of what I'm looking for. Remember? This is the problem with any poll. The majority of Americans now oppose the war in Iraq. We don't know what percentage actually do oppose. We've drawn a sample of them. We'll analyze that one later on today. So the other thing is we've got all these data intervals. Every single one of these is just an experiment, just like you guys did, with varying sample sizes depending on the size of the class. Right? 540. Look how narrow that one is. Look how narrow that one is. Up top, I've collated all the results together. There. That's the confidence interval for all thousands of trials together. Still 95% confident, but now it's this narrow. We're off by a percentage point, if that, left to right, margin of error-wise. So why do I say these results are good evidence that the probability of spinning heads is below 50%? What do you think, Linz?
Because most of the red lines would be for the 1/2, like 95 of the red.
Exactly. Ish. 95. These guys, all these guys, are below 50%. A few of them cross over. And the ones that cross over, I can't decide. The ones that cross over could be 50%. They could be over 50%. They could be under 50%. I can't decide. But like, for example, your trial that we just saw down here, 39 to 49%. It does not touch 50. If it doesn't touch 50, that means I'm 95% sure, I'm 95% confident that 50% is not in the interval. Which means unless I made one of those 5% errors, confidence is tied back to the idea of screwing up. 95% confident means you're 5%, if you will, non-confident, which means you're allowing for that uncertainty. Unless I fell into that outlier set, I'm 95% confident that the proportion of times you get heads is actually less than 50%. It's actually less. Michael?
It's because the sample that you do each time changes because the pennies can change, the people change, and you could just wind up with a whole sack full of bad pennies.
That's true.
And that would
Oh,
change.
sack full of bad pennies. There's a band name in that somewhere. I actually use the same pennies each time.
Okay.
It's the same penny. I use the same bag of pennies each time.
So bad students then.
So now there are plenty of experimental issues. Like, for example, how we spin the penny. I don't think it's that big. I thought about this. As long as the penny gets spinning on a flat surface, I think any inconsistency with how it got started is washed out. I think once physics kicks in, it's going to override. But speaking of physics, can anybody think of why the heads show up less frequently than tails? We get tails more than we get heads, according to most of these intervals, right? What do you think, Susie?
Maybe it's weight.
Good. In what way?
There's more weight because of the...
There's more weight on the head side. The head side has more weight. Why the hell would heads pop up then if it's got more weight? What do you think? What do you think? Christian?
Because of gravity, like the same thing with toast, like with butter on it.
sudden.
If you drop it, it always lands on the side with butter.
Because butter's heavier.
Yeah.
Okay, but this is the opposite of that. Heads are heavier, but they're landing heads up.
Oh, well, don't have a good reason.
No, I love the buttered toast, by the way. I love that. Do you have to spin it to do that?
No.
Just drop it. Do you drop it buttered side up, and then it kind of corrects itself and
It's
falls?
never been intentional.
I have a new test for next term. Thank you. I'm going to get sponsored by the Wonder Bread Company and some kind of butter company. Everhard's. Keep a logo. Keep a logo. Get Great Harvest and Everhard's, and we'll get some buttered toast. And we'll have to apologize for the floors when we're done. So, but what do you think? Why would heads, if heads are heavier, why are heads landing, right? If you think if heads are heavier and the buttered toast, they would land down more. Which means does that make sense?
But we do get more chips, right?
Right, but the problem is the buttered toast, the heavy side lays down. This is the heavy side, if you will, is not laying down more.
The heavy side is the heavy side.
The heavy side is the head side, which is landing.
And we get that left.
Oh, I'm sorry. I'm so confused. This is actually agreeing with it. How about the spinning, though? This is why I asked about how you drop the toast. The spin, my guess is that the heads want to not give up, the tails give up more. See, this is why I asked about how you drop the toast. Do you spin it or do you just drop it? I think the spinning,
I'm on a whole other day.
your whole, what's yours, Beth?
I'm thinking that it would depend the time of the month that you do it. The moon, as it changes, the gravitational pull may be different.
That's water, though. That's like tidal changes.
Yeah, but I'm wondering if it might have something to do with it.
Well, I mean, anything could have something. I can argue against that just because we're talking about tidal differences there, which is like a liquid difference. I was thinking just inertia. Just inertia. Once something gets moving, it tends to stay in motion. The more massive side is going to stay in motion more, if that makes sense. So the tail side, if you will, gives up easier, whereas the head side keeps spinning until it spins all the way down. Does that ish make sense? So that's just an argument. That's just an argument. I mean, I can't disprove nor prove the moon because I haven't tested the moon side.
According to your numbers, we still had more tails than heads.
No, I'm not. We're still. Yes, I'm saying we've gotten fewer heads than tails. I'm trying to explain why. I can't explain why. I have hypotheses as to why.
We're going down
So the weight of the head is bringing it down as opposed to bringing it up.
The weight of the head is pulling the coin down because
Right,
it gives up less than the tails give up.
Right.
That's why I got sidetracked asking Christian about how he dropped his toast. That's why I was trying to figure out if it spins or not.
That has tidal things on the moon, the butter and the moon.
I love this. I love this tidal thing on the moon. Anyway, I want to revisit where the 5% came from, because I want to go back to Ian's question too. Ian's question was, wait a minute, if it's 95% confident, why aren't all these intervals 5% wide? It actually ties back to what Darla said. So what I want to do is I want to take a visit over here. I want to take a visit over to the sideboard. We can cut this off for a second. This entire experiment is based on the idea of a binomial distribution. Heads or tails, fixed number of trials, 430, 10 at a time. So there are two components to this experiment. There's p hat, and then there's the margin of error. So I want to go back and revisit the binomial. Revisit the binomial. Now, when we discussed the binomial in 243, there were two parameters that we talked about a whole lot. The average and the standard deviation. The average and the standard deviation. We call the average mu. So this is for the population. Now remember, we're being a little bit whimsical here because we don't know what our population values are for our experiment. But it ties back to this when we actually assess it. The population, the average, was defined to be the sample size times the proportion of success. Again, a little bit fictitious because we're assuming we know what little p is. Now, when we were doing our experiments, we did know this. I was told things like 90% of birds are female. I was told things like when Max is guessing and putting his Crocs on, it's 50-50. So we could assume parameter values. The standard deviation, which we used less, and if you don't remember this, it's totally fine, is defined to be the root of n times p times q. The root of n times p times q. Okay. So these were, and we didn't use these hardly at all in class. I mentioned them in class as we were kind of going through, We used to use technology to get these extensively. However, I want to revisit these because they help explain where that margin of error comes from. Where that margin of error comes from. Now, this is population value, and these are purely descriptive. They're purely descriptive. It is if you know what P is and you know what N is, these are all determined. The problem is when you move from that to a sample, you have to kind of revisit the idea of what these things are called. You have to revisit the idea of what these things are called. For example, our sample revolves around P hat, which is defined as x over n. Now, if you look at P hat equals x over n, and you look at mu equals n over P, you can see the relationship between them. If you were to divide both sides by n, you're going to get P equals mu over n. P equals mu over n. That makes sense. Mu is going to be the average number of successes. N is going to be the total number of trials run. And that's going to be the probability of success on any given trial. So if you rewrite this as mu over n equals P, which is still descriptive, still part of the population, you can see how this ties directly, as we cross into the sample, to P hat equals x over n. It's the same thing, but not in a purely population-driven way. It's the same idea. Average number of successes over n. Now the difference is, it's not so much an average number of successes anymore, it's the number of successes in your sample. Which is why we changed the language to P hat versus calling it P. I understand these are very, very close, P hat versus P. They mean two totally different things. Sample versus population. Mary, go ahead.
Wouldn't it be x bar?
It's a number. No, it's not. That's a very good point. It's just simply the number of successes you got in your trial. That's why I said here it's an average number of successes. Here it's just the number of successes in your trial, which I know it seems like a strange distinction to make, but it's just you've counted up. We got 189 of them in our trial. 189 and no more. Is that fair, Mary?
Yeah.
It's a very, very good point. Michael, go.
I'm just curious, maybe I've just forgotten what Q is.
Q, you haven't forgotten, because we very rarely talked about it.
Okay.
Q and P are complementary probabilities. So in other words, if P was the chance that we got a girl when we bought a chick, Q was the chance we got a rooster.
Oh, okay.
So they're just, if P is 0.9, Q is 0.1. We very rarely used it in 243, because you just ran dist fill most of the time. So N's your sample size, and P and Q are simply your probabilities of success and failure. Is that fair? Great, but you used it quite a bit on that first day when we were building the distributions in 243. 1 bird, 2 birds, 3 birds, 4 birds, all those 0.9s and 0.1s being multiplied together, all those 0.1s were the Qs. I just didn't bother calling them that. Now, it's helpful here because it's going to help us discover what the wings are. So here's your center. I'm going to call this the center of our margin of error. Excuse me, the center of our confidence interval. This guy here is a measure of variation. He's going to help us get our wings. Well, you know what helped pretty well? When we divided this, both sides of this by n, it kind of helped us come over here and get ourselves a center. Let's do the exact same thing. To make the standard deviation part of the sample, first of all, somebody used an awesome term back there. Somebody said standard error earlier. Who said that? That was fantastic. I heard that phrase. Ben, thank you, my friend. It's going to be, if you will, the inferential version of the population standard deviation. Chris, not to keep bringing this point up, but when you asked about the sample standard deviation earlier, I wanted to differentiate right then between that, which is a descriptive value, even if it's about the population, and the predictive value of the standard error, which is I now have a sample, but I want to predict something about the population. So I'm going to call that standard error, just like Ben did correctly. So I'm going to take this bad boy, root NPQ, and I'm going to divide it by n, just like I did up top. So essentially what you're doing is you're averaging the error. You're averaging the error. I'm going to do a little teeny tiny bit of algebra, if it's okay with you guys. Just a smidge. Just a smidge. Just a little tiny bit. But there's too many n's. I want that down to one n, if that's okay with you guys. Is that okay? A little bit nice. Yeah, okay. So that's got a radical. This doesn't. Can I put this so it has a radical? NPQ. That's going to have to be n squared, isn't it? To put a radical around it, I've got to square it to kind of cancel that. And then what's nice about that is you've got an n here and two n's here. I can knock this one, and I can knock that one, and I'm left with just PQ over n. The square root of PQ over n. That is one standard error. This is one standard error of the sample. One standard error of the sample. Now think back to 243. One standard error of the sample. What percentage of data is going to trap within one standard error? Assuming a bell curve, you get about 68%, which means I'd have to accept no more than 68% confidence. That's not enough. That's not enough. That means you're wrong basically 1/3 of the time. That's too much wrongness. So in order to get 95% confidence, we're going to have to go to 2 standard errors, aren't we? So the first thing I want you to do right now, friends, the first thing I want you to do right now, I want you to calculate. What's the matter, Michael? Go ahead.
Oh, never mind. I thought, I was thinking square root, and then I was thinking we were squaring it again anyway.
Oh, no. You can square it again to get the variance.
Right.
I do want to make one tiny adjustment that I blew through this without thinking too quickly. These should all have hats on them. I apologize. Those should all have hats on them. As soon as I crossed into the sample, I have to accept those as estimates drawn from the sample, which is p hat, q hat, p hat, q hat, p hat, and q hat. Does that make sense? Apologies for getting ahead of myself. N is still standing for sample size, or in this case, trial size. So it's p hat, q hat over n. What I want you to do one time and one time only with me is calculate this for our coin spin experiment. Calculate this for our coin spin experiment. So I'm going to come over here and do it on the TI.
Real quick.
Yeah, Jamie, go.
Saying that the standard error equals 0.39. The root p hat times q hat over n.
Yes.
And that's one standard error.
One standard error, which would be, imagine your bell curve. You're such a limit theorem bell curve.
Error, though?
Say that again.
It's one standard error of the
Of the sample mean, which in this case is p hat. We shouldn't really call it a sample mean, it's a proportion. So that gives you one standard error around that center, which is only 68% of the data. Is that fair? So what I'd like to take a look at right now is, based on our results, the 189 and the 430, I want to calculate that one standard error for our results and see what it comes out to be. Now this is a mess. Go ahead, Chris.
So it's 0.44, is p hat.
That's p hat.
Q hat would be 0.56?
0.56, exactly. So Chris is already one step ahead of me. So to calculate that for our data, and I'm going to try to get, because the TI has infinite, as basically 100 decimal places of precision, rather than calling that 0.44, Chris, would it be okay if I did it 189 out of 430, which is ish 0.44? I mean, this is rounded off. I'm going to try to get to as close to the TI's value as I can. So I'm going to use as much precision as I can. That would be p hat. Q hat would be whatever's left over, which would be 200 and, I can't do it in my head. Let's just do it this way. 430 minus 189 over 430. Too much subtraction early in the morning.
More parentheses.
2 parentheses?
I got them.
You've got one in the middle, though.
No, yeah.
Right? So this one and this one and this one and this one, and then this one and this one.
Okay.
So that's the numerator. That's p hat times q hat. Dividing that by 430, that's the divided by n bit. And then taking the square root of that. All right. About 2.5%-ish. About 2.5%-ish. That's one standard error. Remember what our margin of error was in our experiment?
5.
And doesn't that make sense? It should be twice as wide. Because you've got to bump out one more standard error to pick up the extra 2.5. So 2.5% gets you out one standard error. 2.5 more gets you out the other. It wasn't exactly 5. We rounded it. It was a little bit below 5. This is about 2.4%. So it's about 4.8. We're being a little bit general with our rounding, which is totally fine. It's absolutely fine to do that. So there's one standard error. There's one standard error for our experiment was about, I'll just do an approximate, about 2.5%. But the margin of error, which is 2 standard deviations, this is where the 95 comes in, Darla. To answer your question, this is where the 95% comes in. When you say 95% confident, that means you're bumping out 2 standard errors. It's unfortunately coincidental that 1 standard error is about 2.5%. You can see now why this depends on your sample size. Because you're dividing by n. If n is larger, if you do more and more and more trials, n gets bigger and bigger, what's going to happen to your standard error? It's going to go down. Does this ring a bell from 243? Heck yeah! As your sample sizes go up, what happens to the curves? The curves do this, and the curves do this. If the curves do this, that means their standard errors are crunching in. That's exactly why. Let me turn this off for a sec. Oh, and by the way, you'll never do this again.
Oh, I was just gonna say.
You'll never do this again.
There's
That's
no
just,
way everybody-
friends, you don't have to. That was the whole point of running one prop z int. That does it for you, right? That was the whole point. When you type in, here, let's just do it again. Watch this, watch this, watch this. I'll do this quickly because it's not important for you to do this. But it proves the point to answer Christina's concern here. If I run one prop z in again, but I go to 68% confidence instead of 95, this will bump out 1 standard error. Ish, 1 standard error, right? Notice, roughly 5% wide, which means it's 2.5% on either side. That's your standard error you just calculated. You will never have to run what we did with this times this over. But I felt like a buffoon last Thursday saying we're going to end up with technology and then being like, okay, that's good enough. They now get it. No, you don't get it. That's the getting it part over there, is understanding why this is doing what it's doing. I'm not saying you have to do it again. I need you to understand once why it works. Just like Bert and Ernie with standard deviation. Without that example, you have no idea of why it actually works, why it makes sense. Of course, now I've successfully glazed you like a donut. So let's take 5, walk around a little bit, and we'll come back and kind of try to formalize this in even more. Yeah. Yes. Don't worry about the arithmetic. The arithmetic is just a sidebar. I wanted you to understand where the 5% came from. I also wanted to answer Darla's awesome question about why it's 5%. As you'll see, the 5% or 4% or 3%, all these numbers change depending on how large your sample is. They also change depending on what your proportion is. You may have noticed that, you may not have noticed that. This is the standard error in the sample right here. So the sample size, as the sample size goes up, this whole thing goes down. But as these numbers change, it changes as well. So for example, if you draw a sample of 1,000 twice, and in one of them, p hat comes out to be 10%, and in one of them, p hat comes out to be 40%, you're going to get 2 different standard errors. Because 40% times 60% is 0.24, and 10% times 90% is 0.09. So the smaller, or I should say the smaller, the more extremely different p hat and q hat are, the smaller this all gets. More on that in about 30 minutes. We'll come back to that. That idea might not be inherently obvious to you right now. More on that in about 30 minutes when we kind of wrap up the day. So basically, the larger this gets, the smaller this gets. And eventually, standard error is going to shrink down. That's why when you looked at the, turn it back on over here, when you looked at the results from over time, these fairly wide, definitely varying in widths. The wider ones are the smaller samples. The narrower ones are the larger samples, because the standard errors are shrinking as sample size gets larger. Yes, Susie?
Sorry, I'm just a little confused. You earlier said that with 95% confidence, you could say that 19 out of 20 of these trials would fall within...
On average.
On average.
Right. So I've only got about 26 or so trials.
Because 2 of them don't.
2 of them don't what?
Fall within the standard, or the error.
When you
margin of error. No,
when you say, what are you saying falls, when you say fall within, what are you talking about falling within?
E.
The 39 to 49, is that what you're saying?
Yeah.
The 39 to 49?
Yeah.
That was our trial. So what this means, Susie, we're going to come back to this in about 5 minutes. What this means is I'm fairly confident, 95% confident, that whatever the probability I'm looking for is in here somewhere. Now notice, some of what's in here is also in these.
Okay.
So what you see up at the very top is
the amalgamation, if you will, of all of them. That tiny little interval right there. Now, I don't have the actual values in this interval, but it appears to be somewhere between, say, there's the historic p-hat is 43%. Looks like about plus or minus 1% or less from that. So when you say falls within, when you get your sample, the best you can say is, I'm 95% confident that it's no less than that, but no more than that. That's the best you can say. You don't know where it is in there, but you're 95% confident that it's in there somewhere.
And that changes for every sample.
It has to. So, and what's interesting you bring this up, I saw a gentleman from New Zealand actually give a talk on tossing this whole idea of confidence intervals and instead just focusing on this, where you run random samples over and over again and eventually look at the intersections of where all the intersections are, which essentially is what happens up here. You're looking at a more refined view. So you're cutting off these tails that are too low and too high and focusing on the ones that share the commonality in results. The problem with that, and it's an overly simplistic view, is you get one of these. You don't get to run, say, randomizations infinitely ad nauseum, necessarily. You spin the coins 430 times and you get your results. So all you have, well, I scrolled down, is the 39 to 49%. So, but the best you can say is, I'm confident that it's more than the 1/3 that was given to me, because 39 was the low end, and it's less than 50% because 49 was the high end. I can say those two things. I can challenge those two claims. I can't challenge many other claims. For example, if I know, let me mute this down here. If I know that I'm 95% confident, that the proportion of heads landing up is between 39 and 49%, I can challenge both the 1/3 and the 1/2.
But that's only in ours. Because
sure, but that's what I'm saying. This is what I've got. This is the sample data I've got. So my claim is this 1/3 is too low to be believable by our data, and 1/2 is too high. What I can't do is, say for example, criticize 40%. Or 41%, or 43%, because 43 and 40 and 41 are still within there. More on that to come to in about 5 minutes as far as totally analyzing those individual pieces. Actually, you know what? Let's just do it right now, because this question leads into it naturally. We'll come back to the restrictions in a second. Let's take a look at some headlines. We'll come back to this, and we'll go straight into, we'll deal with that in a second. All right. So here, there we go. This is a bit dated now, but it doesn't matter because the point stands. Go ahead and read this. This is related exactly to the more than half now are opposed to the war in Iraq. Gesundheit. Your take on this. Your take on this. What do you think? What do you guys think?
Who cares?
Who cares? Okay. Who cares? Gallup cares. And people that use this to create media outlets care, perhaps. What's your take? Ashley, go ahead.
With the sampling error plus or minus 4 percentage points, the 50% is not that symbolic because you can easily get 46%.
Exactly. Exactly. You have to realize something too. When I put this all together for you, this is spread out over the course of an entire website. I've taken these pieces together and kind of shoved them together. This is going to be hidden near the bottom of all these sites. So basically, what you have to do is when you very tiny writing, usually gray, not in the black color the rest of the font is. You have to envision it like this. There's 50% right there. Plus or minus 4% is going to look like that. So basically, to re-answer Susie's awesome question, I don't know what Obama's approval rating is. Because it's a mystery. I can't ask 100 million, 150 million Americans. But what I can do is I can take this random sample of 1,544 adults. The center of that sample was 0.5, according to that 50%. That's what that means. Reaches 50% for the first time since spring. Okay, what they mean is, in the sample they drew, p hat was 0.5.
Yeah.
That's what it is, p hat. Then you slap the margin of error on there. This is actually a standard error. The margin of error is going to be 2 of those. Did you catch 95% confidence?
Yeah. Yeah.
One can say with 95% confidence. That's why it's 2 standard errors, which means 1 standard error. If 2 is 4, 1 would be 2.
Right.
They double it, make it 4%. So a better thing to say than Obama's approval is at 50% is that Obama's approval is between, good, that's even easier than I was going to say, between 46 and 54%. I was going to say no lower than 46, but no more than 54. I like between better, it's more simple. Michael?
Well, I don't understand how the margin of error in this particular sample is so low.
Actually, I don't understand. I think it's too high.
You think it's too
I think, hold that thought.
Okay.
Give me 25 minutes.
Okay.
Hold that thought. It's a great question. I think 4% is actually too high. I think they rounded it up.
Okay.
We'll come back to that. We'll come back to why I think it's actually higher than it should be. Now, obviously, it should be less than ours from our experiment, correct? Because all things being equal, which they're not, they did a sample of 1,544. We did a sample of 430. So tops of the fractions being equal, theirs should be smaller because they have a higher sample size. The n in the denominator is larger.
But the total population is so much larger.
That's irrelevant. Hold that. 25 minutes. That's irrelevant. And I promised you this in 243. That it's irrelevant. I promise it'll be resolved today. I promise you this.
Okay.
Awesome. Chris?
Well, 2 things. Your mic is unplugged.
That's okay. I was doing an A-B.
Okay. The other thing is, they say reach 50%. So you're basing your graph on 50% plus or minus 4. That can
Yes.
mean he just reached 50% with the plus 4.
You know what else?
So
That's true. That's true. Like with this, right?
Yeah.
My point, the whole just reach is another argument. Because if you actually look at the tracker from before, this whole argument applies to the ones leading up to 50% as well. If it's at 48% plus or minus 4, and they say he's below 50%, you say not necessarily. He might be above. 48% plus 4 is 52%. Now, Christina's question still is out there. Maybe we don't care about that. But any poll reads this way. Any proportional confidence interval reads this way. Jared, what was your point? You had a point a couple minutes ago.
I don't remember.
You don't remember? Damn it! I love to go and turn, and then I get lost. So this helps some students think about it. See that fish? That fish represents basically all potential values of what you're trying to estimate equals. You're trying to estimate Obama's approval rating. Think of that as a point inside this interval. All you know is it can be one of those points, like a fish swimming back and forth in this green tank. You don't know where the fish is, but the fish could go as far as this side or as far as this side.
And it depends on the day.
And well, that's true. It depends on a number of factors. But based on this particular survey, that's the best answer you can give. So this helps some students. Think of it as a fish going back and forth. The fish is the parameter. The fish is Obama's approval rating in the approval rating in the population. The fish can go back and forth. Fair enough? Good enough? Fair enough. Okay. I'm going to use one more. This one is an older one, and I'd like to can it eventually, but it drives the fish point home. War on Terror update. 34% of likely voters, it's getting old, it's probably outdated, but that's okay. 34% of likely voters believe the situation in Afghanistan will get better. 39 expect it to get worse. Okay, now 34 is obviously less than 39. Do we believe that it's significantly less? And when I say significantly less, does it hold up to margin of error analysis? Look at the margin of error.
Yes.
Yeah.
The margin of error is 2%. So what do you think, Karen? You're saying yes, it does?
Yes.
Tell me why.
Well, because if you take 2 away from 39, you're at 37, and they're saying 34. So there's a 3% gap in there.
So between 34 and 39 is 5 percentage points. So if you come out halfway from each, that would be 2.5 percentage points. Because the margin of error on the poll is only 2%, this 34 could be as high as 36 or as low as 32. This 39 might be as low as 37 or as high as 41. But even though this one at its lowest is 37, this one at its highest is only 36, which means there is a minimum significant difference of 1% there. Which means I do believe that more people think it's going to get worse than get better based on this survey. There's no overlap of intervals, which means there's no... Think of the fish. Can the fish in the war gets worse tank, can that fish ever get into the war will get better tank?
No.
Can't. Not based off this sample data. Not based off this sample data. So I'm not saying that every poll is crap. I'm saying that read for margin, if it holds up to margin of error analysis, then you can say that there is a significant difference. It's a statistically significant difference. Otherwise, it's just a difference. It's, in other words, a non-statistical difference. Yeah, 34 is less than 39. Yeah, but is it significantly less? That says yes. Go ahead, Michael.
We only have 83% of the results.
Say that again.
We only have 83%.
Then you have to analyze the other, whatever it was, 83, the other 17%. But that 17% is probably a no opinion.
Okay.
That would be down there far down, with the same margin of error of 2%. You see what I'm getting at? 17 plus 2 is 19%. It's still not touching the other two intervals. Good point. Good point. Go ahead, Susie.
Now, if you wanted to go out 3 standard deviations, then it wouldn't be.
That's a fantastic point. Suppose you wanted to go out 3 standard deviations. What confidence would you be at that point?
98%.
It's at 99.7 or something like that. It's very, very high. There's a reason why we don't do that. And this is one of those unfortunate things. I haven't thought about a way to talk about why you do it right now. But there's 2 ways to be wrong with a statistical inference, both of which we talked about at the end of 243, false positives, false negatives. When you go out too far with a confidence level, you shrink what's called the significance level, and you increase the chance of what's called a type 2 error. That seems like cryptic hoo-ha right now, and it kind of is, because when we start talking about hypothesis testing, it'll make a lot more sense. So 2 standard deviations is used, which means 95% confidence is used almost de facto standard across publications like this, also your research journals you're reading, because it does the best job, on average, of minimizing both potential false positive and false negative errors. If you need to know right now, by all means, I put a paper on the arithmetic page that explains it, but you might just want to wait until we get it in class in about 2 or 3 weeks. It's a great point, but 95% is pretty much, like I said, a de facto, if you will, standard. Is that fair enough? I do want to pull back for a moment. I want to come back to these kind of in the headlines thing, although this one is definitely old, needs to be replaced. I want to take before we go any further, and Mike, you brought up a good point when you mentioned the other case, the other 17%. Before you run this kind of analysis on data, you should really be careful that the analysis you're running should be run. So what I like to start, and this is not the kind of thing that I test you guys on exams, but when I didn't get this PowerPoint yet, I apologize. And I'll have this posted later, you can download it then if you want to. Before you run this one prop z int, before you construct a confidence interval around data, you should make sure you can check off a series of things. First of all, you got to make sure that your data is binomial. You've got 2 results. They're independent, mutually exclusive. And the belief that the likelihood of success and failure are constant. Now, I'm calling those P and Q, of course. I'm calling those P and Q. What you're not seeing with P and Q is the knowledge of what that equals. Because that's what you're trying to do with this tool, is approximate what P equals. Or Q. I guess if you can approximate P, you can also approximate Q. So if you can say yes, yes, yes to all of this, then life is good. There's another concern. You have to make sure you have enough data. And like I said, when I show you this kind of stuff, these assumptions, I'm going to talk about assumptions a lot in this class. I'm not testing you on this kind of stuff like on an in-class assessment, or probably even an out-of-class assessment. But when you're out in the world actually doing these kinds of research methods, you need to know when you can run things that you're allowed to run and when you shouldn't. When you can and when you shouldn't. So you've checked off, yes, it's a fixed number of trials. Yes, so Gallup did 1,544. Okay, boom. 2 mutually exclusive outcomes. Yes, either I approve or I do not approve. Chances of success and failure are believed to be constant. We have no reason to think they're not. This one's a little bit tricky. You have to have enough data. The trick with enough data is that, well, there's a base minimum. There's a base minimum of data points that you need, a bare minimum. And then there's a number that you need to satisfy certain assumptions. And that's what I was talking about with Mike about, as far as you don't have to have a percentage of your population, but there is a certain cutoff that you need. That 1544 is actually plenty, believe it or not. And you don't have to believe it right now. This is the base minimum. You have to have enough trials so that you have at least 5 successes and at least 5 failures. At least 5 successes and at least 5 failures. So n times p, if you remember, and of course you can say no, is the average number of successes per binomial experiment. N times q, which we don't talk about, is the average number of failures. Now, the reason for this is calculus driven, but I think I discovered a way to explain it without using calculus. And I got a little PowerPoint deal I want to kind of run you through to show you why. It all ties back to the shape of the distribution. When we say 68% confidence is 1 standard error, 95% confidence is 2 standard errors, 99.7 is 3 standard errors. What distribution are we really using right there? The bell curve, the normal distribution, right? Well, wait a minute, now time out. This is the binomial. But yet all of a sudden we're launching into the bell curve. Something you may have forgotten from 243, and it's okay if you've forgotten it from 243, is that there is an intersection. There is an intersection of the bell curve and the binomial distribution. There's a beautiful intersection. Check it out, in case you've forgotten. In case you've forgotten, and you may have. Let's back this up. In case you've forgotten, and you may have. All right. This is something we looked at in 243. Here's a binomial distribution. 3 trials, probability of 0.5. There's 10 trials. There's 25 trials, 50 trials, and I think I go to 100. So as the number of trials increases on a binomial, you get this beautiful bell curve that pops out. But this makes an assumption. It makes the assumption that the success rate is exactly 0.5, like Obama's was. How about our penny, when the success rate is shifting, like at 0.43 or 0.4 or 0.3? So I'd like to analyze that next. Okay, so I'm still going to let n go up to infinity eventually. But now I'm going to look at what happens when the value of that success rate changes. Now watch the top curve and the bottom curve as p shrinks. 0.4, 40%, 30%, 20%, then 10%. What's happening to your bell curve? Your bell curve is becoming skewed kind of predictably, but now we can't use it anymore. We can't make these assumptions about 68%, 95%, because the bell's gone now. So this is where that 4th requirement comes in. When your p begins to differ significantly, when it starts to get too far away from what's actually going on, that's when you have to increase your sample size. Here's what happens as we start increasing our sample size. Right now the sample size is 20, now it's 40, it's going to go up to 60, then 80, now it's up to 100. And notice, even when your average is at 10%, let me back up a little more. I went a little too fast. You get your bell back. You get your bell back, even when your proportion is at 10%, highly skewed right, highly leaning left. Some of you may notice that n is 100, and we've lost from 21 out to 100 on this tail. That's because the chance of that happening is next to nothing when you have a success rate of 10%, but you've got your bell back. So what we're talking about is it really doesn't matter how skewed, as long as you can get enough data to invoke the bell, we can then invoke 68%, 95%, whatever percent we need. That's where this bare minimum kicks in. That's where this bare minimum kicks in. It sets up the proper baseline to make sure the bell curve percentages are useful. So if you want to say 68%, awesome. If you want to say 68%, make sure you've got enough data to actually see a bell curve. If you want to say 95%, make sure you've got enough data to actually see a bell curve. One small problem, and this is okay, the one small problem is that P and Q are unknown. That's one teeny tiny problem. We don't know what P is, we don't know what Q is. They're unknown. We're trying to estimate those. We'll come back to that problem when I answer Michael's question in about 20 minutes or so. That's towards the very end, is establishing a proper sample size based on more restraints. So basically, this gives you a baseline to have enough data and the right kind of data. These assumptions, again, friends, I'm trying to get you this class from the point of view of you're going to be using this stuff in your jobs, rather than just passing an exam. This is too nitpicky for like an in-class assessment, for sure. But I want you to go out into the world as statistics users and be able to know what to run. And the only time you're allowed to run this is if you can check all of these things off. So, let's be critical then. Most of the time, in all honesty, most of the time, you're going to be analyzing statistics that you've already seen in other places. We've already done this twice. So what I want to do is I want to launch forward to one more example. Here we go. Again, getting dated. But this one here is the most egregious case, I think, of media not giving you enough information. This was the headline. "52% of Muslim men unemployed, 47% of Dalit men unemployed. Therefore, higher percentage Muslim men unemployed by 5%. No margin of error whatsoever. No sample size, no margin of error. Do I believe that? Do I believe that? I don't know if I should or not, right? I mean, yeah, 52% is higher than 47%, but I have no idea how to believe it. So what I did was, I just started creating intervals. I started creating intervals around sample sizes. I said, suppose the sample size was 100. Let's suppose sample size was 100. So that means this would be the 95% confidence interval of caste versus Muslim unemployment. Notice they're both centered on 47 and 52%. But the margin of error stretches down to, it looks like about 37 up to 57. So you've got a margin of error of 10 percentage points, don't you? 37 to 47, 47 to 57. 10 percentage points both ways, 20% width. And this guy here, also 10%, 10%. Can I tell there's a difference between caste and Muslim unemployment if my sample was only drawn on 1,000? Can I make the claim that there's a higher percentage of Muslim unemployment than caste unemployment, looking at those two confidence intervals? No, think of the fish, right? The fish are the actual parameters. This Muslim fish could be down here, and the caste fish could be up here. So we can't judge anything by that. Let's increase the sample size. Christian, what's on your mind? You just stretch it.
Oh, yeah.
Oh, okay, I saw I look at activity and I see motion. Let's increase the sample size to 500. Can I believe that a higher percentage of Muslims are unemployed than castes with this result? No. Same problem, right? About 1,000. Now, I know it looks like it just got wider. This is something I didn't think about before I took the screenshots. It didn't. The axis just recentered itself. They're actually narrower, they just stretched out more. Can I make a decision right now? No. It's getting close, but there's still overlap. Overlap tells me I still can't make a decision. How about with 2,000?
Yes. Yeah.
Finally, there is a minimum difference between the two of them. But here's the problem. What sample size did they use in their study?
We don't know.
I have no idea. So finally, I want to answer Mike's question. What sample size do you actually need in order to see if there is a difference in what you're studying, or in order to get the estimate of what you're actually studying? Let's turn this off. A little more algebra, teeny bit more algebra.
Wouldn't it depend?
Say that again.
Wouldn't it depend?
On what? It depends on two things, actually, Katie. What are you thinking? No, it doesn't depend on that at all, which is surprising. What is it, when you were making your guys' decisions about whether or not there was a difference in caste and Muslim unemployment, what were you looking at?
The overlap.
The overlap of the intervals, right? What was the overlap determined by? Standard error or the margin of error, right? Is it okay if I call it the margin of error just because that adjusts for a level of confidence? That's what it depends on. It depends on how wide you'll allow your margin of error to be before you start. Hold tight on that. Hold tight on this. Let me get rid of this because we don't need it anymore. So the question of the hour is, how large a sample do we need? How large a sample is needed? Now, we've partially answered this with the restrictions for the binomial. We know that n times p and n times q have to be at least 5. But that's a bare minimum. You saw what happened when I let n be 100. When I let there be a sample size of 100, the margin of error was 10%. That's ridiculously wide. Which means if my sample size is down around 20 or 25, it's going to be 15%, 20%. That's kind of too wide to be useful. So, Jamie, yes, it does depend on something. It depends on two things. It depends on two things. Number one, what confidence do you want to use? What confidence? Usually, we're going to use 95%. Usually, we're going to use 95%. Usually, we're going to use 95%. That's a standard. And then, this is called the confidence level. It's got a special name, which we'll keep using over and over again in this class. The confidence level is usually going to be set at 95%. But because of how you guys were making your decision, it also depends on how wide you allow your actual margin of error to be. So it depends on your maximum desired margin of error. That's for you to choose. That's for you to choose. So you have to ask yourself the question, okay, how much do I want to be off in my estimate? So my study's going to give me a p-hat, like your pennies. Your pennies, p-hat. P-hat, 0.43, 43%. How much do I want to be off? In other words, how much do I want to sway it down or up from 43%? We had to settle for 5% because we had the trials we had. But if you're starting the study and you want less of a margin of error, then you've got to start the study by having more trials. So you have to start right in the beginning by picking, do I want to be 3%, 4%, 2%, 1%? Now, why does that? Nowhere in here is the size of the population. And that's because, think about this, your margin of error is defined to be your standard error times, I'm going to call it Z, if that's okay with you guys. I'm going to call it Z. Why am I going to call it Z? Remember what Z stands for from 243? Say that again. It's a Z-score, Ash. Yes, it's a Z-score. And that Z-score tells you how many, you got it, how many standard deviations from center you go. One standard error is 68% because one standard error, Z would be 1. Two standard deviations would be 95% because two standard errors would be 95%, which would be one margin. Now, the margin of error is dependent on the confidence. This is a general term. This is a general term. So if you're at 95% confidence, it's still a margin of error. 68%, it's still a margin of error. So margin of error is determined by your confidence. And basically, it determines what value goes right there. So let's think about, oh, Beth, go ahead.
No, I just want to make sure I understand this.
Mm-hmm.
Z-score times the
standard error, yes, ma'am.
Equals the standard deviation.
It equals the margin, we're calling it the margin of error. The standard deviation, back to what Chris said earlier, the standard deviation is a descriptive statistic of the sample data. The margin of error is the plus or minus that you're applying to the population. You're saying I can be as low as this or as high as this, so it becomes inferential.
Okay.
Is that this, all this shebang is inferential. That's what makes it kind of cross into 244 from 243. Good connection though. Now think about this. Think about this. Margin of error. You pick that right here. You pick that right here. Equals Z. That's the confidence level that you pick right here. This guy right here, P hat times Q hat over N. Right, exactly, Carrie. This is getting terrifying. This is getting terrifying. There's a lot of variables here. There's the margin of error. There's Z. There's P hat, there's Q hat, and then there's N. Now, one of those 5 variables is what you're actually interested in. What was the question that we asked at the very beginning? So in other words, we need to know what that is right there. Go ahead, Michael.
Is Z multiplied by the square?
It is.
Okay.
It is multiplied by the standard error, and this is the standard error for our experiment right now. So our job is to get that solved for N. Our job is to get that thing solved for N. Go ahead, Jamie.
So is Z just going to be 2?
Exactly. If we assume 95% confidence, Z will just be 2. Hold that thought. Hold that thought for just a moment. We'll come back to that. I actually gave you guys a program in 242 that does this for you automatically. I'll share it with everybody else too if you guys want it. So your margin of error is going to, I'm just going to leave that as margin of error. Z is just Z. And this guy here, we have to reverse engineer. Now, Jamie, I love just calling that 2. Would you guys mind if I move stuff around so that n is actually by itself on one side? Just to make the math easier, because solving for n where n is right now is going to be a pain in the butt. It's going to be an absolute pain in the butt. So I'm going to, let's see, I'm going to divide by Z. So I'm going to have the margin of error over Z. And then I'm going to have this equals this big radical, P hat Q hat over N. I'm going to square both sides. So then I'm going to have, don't worry, square. And then this is going to be P hat Q hat over N. I'm going to flip the whole thing to put N at the top. Well, you can do that. It's a proportion. So I'm going to flip this and flip this, which is all legitimate algebraically. That's legitimate. So you're going to have Z over the margin of error, and that's all squared, equals N over P, oops, that's N, over P hat Q hat. If the algebra's making you nauseous, just sit back and relax for a couple seconds. Now, here's one problem. We got to be careful chicken and egg in here. We want to know, because there's a chicken and egg problem going on. We want to know how large a sample we need. In order to do what? What's the whole point of today?
Yeah, the population.
That's the whole point of today. So in order to estimate the population proportion, we get P hat plus the margin of error. According to this computation, we have to know what P hat is to get the sample size. There's an easy, cautious fix for that. What is the value of P hat that will make P hat times Q hat as large as possible? What value of P hat will make P hat times Q hat as large as possible? Well, let's try 0.1. 0.1. 0.1 times 0.9 is 0.09. Let's try some different values. How about 0.2? 0.2 times 0.8 is 0.16. It's getting bigger. It's getting bigger. How about 0.3? 0.7, that's 0.21. I hear 0.5?
Yeah.
Okay, if we jump 0.5, 0.5 is 0.25. Well, if this pattern continues, we just keep getting bigger. How about 0.6? Ah, that's going to start going back down again. So, the value of P hat that's going to make this product the largest is a half. Now, there's a reason for that. It's a Math 111 a reason. Unfortunately, I've seen enough reactions to the algebra I've done today to draw a parabola on the board and show you why. There is a proof on the original page if you're so interested. It's on there if you want to see it. So, in order to make this as large as possible, and I like the idea of making it as large as possible because it's going to make the sample as large as possible, which makes our error minimized. Let's just assume P hat and Q hat are both a half, which is the safest bet. So if this is a half and this is a half, the whole thing is 0.25. So I end up with Z over the margin of error squared equals N over 0.25. And last but not least, just multiply by that 0.25. And to answer the question, how large a sample is needed, all you've got to do is figure out 0.25 times your z-score, which is tied to your confidence, as Jamie pointed out, in this case it's 2, times your margin of error, and square that. And that will tell you how large a sample you should have to be that confident with no more than that margin of error. Go ahead, Beth.
Is it always going to be 0.25 or just?
Always. Because by using 0.25, you're using the largest possible deviation of the multiplication of P and Q. So in other words, you're putting a safety net in there. You're putting a safety net in there. You're saying, I don't know what P hat is, I don't know what Q hat is. So I'm going to assume they're both a half. I'm going to assume they're both a half. Go ahead, Jamie.
So can you just pick your own MOE?
Yes. What you do is, I want to be off by no more than 3%, by no more than 4%. Let's go back to our penny example. Suppose we want to run the penny example, and we don't like our 5% margin of error. Suppose instead of a 5% margin of error, we want no more than a 3% margin of error. So in other words, we'd have to check our sample size. Let's do this over here. Yep, you have to start by picking that margin of error, Jamie is right. So back to the pennies. Back to the pennies. Suppose we still want 95% confidence. Still want that, for sure. So C's going to be 2. You got it. You got it, Carrie. But now we want no more than a 3% margin of error. No more than a 3% margin of error. 5% was too wide. We're clearly going to have a larger sample size than we did originally. Clearly. But how much of a sample size are we going to need? Well, that's what this calculation shows us how to do. So that sample size needed is just going to be the 0.25 times the z is a consequence of the confidence. Z is going to be 2 for 2 standard errors over the desired margin of error. And this is why I wrote the program. This is why I wrote the program, which we'll illustrate here momentarily. Margin of error is 3%. It needs it as a decimal. It needs it as a decimal, and that's extraordinarily easy for students to goof when they're inputting it. Extraordinarily easy. You have to square the whole shebang because of the undoing of the square root. That's very, very easy for us to screw up. It has to be a percentage because of the way the mathematics of the units here. Percentage times a percentage times a percentage rooted is equal to a percentage. So it has to be in the form of a percentage to get to that point. Well, let's figure out how large of a sample we need. Let's figure out how large of a sample we need. Clear a little board space. Go ahead, Gary.
We just don't know what that word is between sample and...
Oh, sample size. Sorry. Sample size. Yep, sample size needed. So let's calculate it. Let's calculate it. I'm going to do what's inside the parentheses first, 2 divided by 0.03. And then I'm going to square that. And then I'm going to multiply that by 0.25. So go out and get roughly that many coin spins. That'll get you no more than a 3% margin of error. It might actually be less than a 3% margin of error. That margin of error is dependent on the size. It's dependent upon the size. P hat and Q hat both being 0.5. If your study comes back not at 0.5 and 0.5, if it comes back at a different value than 0.5 and 0.5, then your margin of error will actually be less. It'll actually be less. So this is the maximum desired margin of error. No more than 3%. No more than 3%. Go ahead, Susie.
With 95% confidence.
With 95% confidence. Now, technically speaking, we used that 2. Technically speaking, that 2 is actually closer to 1.96. And that's why, rather than having to keep all this stuff memorized in our head, I did write you this. We're going to break class a little bit early so I can give it to the folks who don't have it yet. If you guys look in your program list that I gave my students in 243, and I'll give it to the rest of you guys at the end of class here. Go down and find one called Sample Size Calc, SSZE Calc. SSZE Calc. If you didn't clear your memories from 243, it'll still be in there. If you grab that and you run it, it's going to ask you for your confidence. It's going to ask you for your confidence. You can put either 0.95 or 95. It'll accept either one. And then you put in what your margin of error is. So in this case, we're using a 3% margin of error. 3%. It's going to tell you to go get 1,068, the sample size of 1,068. Notice it's a little different than what we got. That's because 2 isn't really 2. 2 is more like 1.96. If you actually run that computation with 1.96, you'll get 1,068. And that's kind of a magic number. 1,068 will get you 95% confidence and no more than 3% margin of error. Yeah, that. Go to your program. Just like this fill, this draw, all those. It's down there. So if it's not, that means you erased it, and I'll give it back to you happily.
So is that for
Any proportion study. Anytime you're trying to estimate the proportion of something, that's the shebang that gets the job done. Yeah, that gets the job done. That's okay. A lot can be said in an hour and 45 minutes, so it's helpful to say things more than once. Let's continue this discussion on Thursday and wrap it up then. I got a couple examples we didn't get to today. I want to make sure we get to those. So I'd say knock the quizzes out for Thursday. Don't worry, if you want to start looking at this homework, that's totally fine. But I do have some more examples I want to run in class with you. I'd rather do that together before I kind of set you loose on the homework. If anybody wants these programs, stop up here and see me. We'll get them off. We'll offload them to your machines, and then we'll catch you then. What you got, bro? Oh, sure.